Let's define bandwidth and relate it to the quality factor of a resonant circuit. If you remember our parallel RLC, the voltage response was a maximum at resonant frequency omega naught, which happened to be equal to 1 over the square root of LC for a parallel RLC circuit. Before we go into the bandwidth, let's jump back and just take a look at our admittance equation for the parallel RLC. If you recall, we looked at our admittance in terms of a function of S, and then when we solved for that, we substituted in our alpha, our omega naught, and omega d, and we found that we had zeros at S is equal to negative alpha plus or minus j omega d, and a pole at S is equal to infinity. So we map that on our pole zero constellation. We look at our critical frequencies here at negative alpha plus or minus our j omega d, which is our alpha squared minus omega naught squared. And for our underdamped case where alpha is less than omega naught, that's what we're really considering for resonance, where we're in the second quadrant here of our imaginary and real axis, or our j omega versus sigma axis. So our zeros are off the real axis, and we have an exponentially damped sinusoid, and we get pure resonance when omega d is equal to omega naught. This alpha is equal to 0. When we pull these zeros closer to our j omega axis, that means our alpha gets closer to 0, and that we have less resistance, or excuse me, more resistance in our parallel RLC. Our critically damped case is when alpha is equal to omega naught. So when alpha is equal to omega naught, our quality factor is just going to be equal to 1/2. So our quality factor anywhere between 1/2 and when our quality factor goes to infinity, that's when omega naught is equal to omega d and our alpha is equal to 0. So this is the range at which we're considering resonance. So we need to have a quality factor greater than 1/2 to have a resonant circuit at all. Otherwise, what we have is the overdamped case where alpha is greater than omega naught, and we end up with zeros on the real axis at sigma is equal to is equal to negative omega naught to the right and left of that. So this is not a case when the quality factor is less than 1/2. That case is not considered for resonance. So now we're going to be relating this underdamped, critically damped, overdamped cases that we've explored to our resonance circuit and our bandwidth. So again, what we're really going to be considering is an underdamped case. As critically damped is the boundary condition where we have to have a quality factor greater than 1/2 is what we'll consider it now. So if we go back and look at what we want to explore is our bandwidth. That's the frequencies to the left of or less than omega naught and to the right of or greater than omega naught with which the resistor will absorb half the power that it does at resonance. So we call omega 1 our lower half power frequency and omega 2 our upper half power frequency. So our average power absorbed in our resistor, we can use the voltage Vm squared divided by R, so that voltage across the resistor squared divided by the resistance. We're not using RMS values, we have to use our 1/2 factor because remember this is sinusoidal steady state condition. So that's going to be 1/2 of our power at resonance. So that's going to be 1/2 of then our VMR when that sub naught, that's at resonance divided by R, and our VM, that VM of the voltage across the resistor, then that's what's going to be the 1/2 factor. That's the only thing that can change. So that VMR itself is then equal to the square root of this, so it's 1 over the square root of 2. So that's that. Here's the square root of 2 where that our Vm is in fact our magnitude of I times R at resonance. So that's why we have that square root of 2 for the voltage, so we get the half power. So the actual width of the response curve is from omega is equal to 0 to omega is equal to infinity. The half power bandwidth measures the portion of the response which is greater than or equal to 70.7% of the maximum value. For a given resonant frequency, the larger the quality factor, the smaller the half power bandwidth. So that means we have a steeper curve here. So our high Q circuit leads to a narrow band and a steeper response curve at resonant frequency. So we can derive um, our bandwidth from our admittance equation. And so what we're saying is our bandwidth, that's the difference between omega 2 minus omega 1, and it's equal to omega naught divided by Q naught. If you recall, alpha was 1/2 omega naught divided by Q naught. So our bandwidth is actually 2 times alpha. So again, if we start out with our admittance equation, evaluating that at j omega, as opposed to our admittance as a function of s, we'll just say s is equal to 0 plus j omega. So we'll evaluate it at j omega. Then we get, 1 over r plus j. We have our imaginary part here. And then what we want to do here, we'll just do a little bit of manipulation, and we'll pull out a 1 over r, so we have to multiply by r, and then we'll multiply numerator and denominator by omega naught. We can do that. That's just a 1. When we do that, we can also look at our quality factor. Our quality factor, that's omega naught RC, or it's equal to r over the magnitude of our inductive reactance, or r over omega naught L. So r over omega naught L we have here, omega naught RC we have here, so we can substitute our quality factor into this equation, and we get our admittance is equal to 1 over r plus j times 1 over r, and then this term in here, which is omega times Q naught divided by omega naught minus omega naught times Q naught divided by omega. Again, omega is our operating frequency. Omega naught, that is that's the resonant frequency for a parallel RLC. That's 1 over the square root of LC. So at omega is equal to omega naught, we get a y is equal to 1 over r, because these will be the same. They cancel. We'll get a Q naught minus Q naught, and we just this is going to go to 0, and we get a totally real admittance of 1 over r. At what frequency is our admittance equal to the square root of 2 over r? That's what we want to look at to derive this omega naught over Q naught as being our bandwidth, because that's our bandwidth when our admittance is going to be the square root of 2 over r. That's when our voltage response will be the square root of 2 times our maximum. So when we to find that half power bandwidth, what we're doing is we're taking this equation, and we've just pulled the j Q naught out, and we set that equal to the square root of 2 over r. But we have the 1 over r here, so the r's cancel. So this term here then is equal to the square root of 2, which means that underneath this radical, that must be equal to 2. So this is a 1 squared, so that means this must be equal to 1. So our Q naught times omega over omega naught minus omega naught over omega, that can be plus or minus 1. So we get 2 positive radian frequencies, which gives us our bandwidth. So this is the solution for these 2 positive radian frequencies. If we take the difference of these, that's where we get our bandwidth is equal to omega naught over Q naught. And I'll leave you to do that last step of algebra on your own. So this we can derive. We derive this from our admittance equation easily enough. Exactly what are our half power frequencies? They're not necessarily going to be symmetric around omega naught. It depends on the quality factor, but it depends on the quality factor. But what is true is that our omega naught squared is the product of the two. So or omega naught is the geometric mean of the product of the two, the square root of omega 1 times omega 2, and our bandwidth is omega naught over Q naught. So we've said when we're talking about a resonant circuit, the 2 most important characteristics of the circuit are the resonant frequency and the quality factor. Well, additionally, what's also important is the bandwidth. So we have here how they're related to each other, and we can also talk about these half power bandwidth frequencies. So the next video we'll look at how we can, if we have a high Q circuit, how we can look at high Q approximations.